Okay, so we're in 3.5 and we're talking about irrational and complex and imaginary numbers. Okay. So we talked a little bit about like graphing numbers and how to graph them. So here we're going to talk about this big idea. So big idea number one, the set of numbers that contains all rational numbers and all irrational numbers is a set of real numbers. And the location of a point on a number line can be represented by real numbers. So I just want you to think real numbers are every single number you know to date. Every single number. And so I've shown this. This is from another one of my classes. Hold on, let me just pull it up over here. So in another one of my classes, I made this chart for them, and I think I showed you before. I'm not sure if I did, if it was your class or another class, but this is like a chart that I made for them. And if you look, this is every single number that you know. And these are actually all the numbers you will ever learn. We are going to be going into this area called complex numbers in a little bit. So we talked about natural numbers. Those are the numbers that are counting numbers. So these are numbers that like you first learned how, like what numbers were. So that's 1, 2, 3, 4, 5, 6, all the way up, right? And then you learned about whole numbers, and a whole number is all of the natural numbers with the number 0. Okay, so it's a whole number is anything that I could describe a whole something. So for example, a whole pizza, a whole phone. So if I have like a part of a phone, hey, Miss Johnson, I have half a phone. No, you don't. You have no phone. You have 0 phones. Okay, you don't have 0.5 of a phone. That doesn't make sense. Integers are the numbers that are on the number line, and we usually see them as -2, -1, 0, 1, 2, all the way up, right? And then we get to, oops, I didn't mean to move this. And then we get to rational numbers. Rational numbers, I like to call them fractional numbers. And fractional numbers, and if you've ever seen a Venn diagram, sorry, I'm assuming that you've seen a Venn diagram before. And so what a Venn diagram is because this pink circle is completely in the purple circle, that means that every pink number is in the purple, right? Every natural number is a whole number. So usually the way I describe this is like cities and then their counties and stuff. So let's just say that you lived in Anaheim, right? Or we're talking about the city of Anaheim, right? Anaheim is where Disneyland is, right? So every single person who lives in Anaheim, right, also lives in LA County. Wait, is Anaheim LA County? Shoot. Okay, I'm going to do Long Beach because I can't remember if, I think Anaheim is Orange County. My bad. So we're going to do Long Beach. So this is Long Beach. Sorry, I usually use the city that we're from, but I don't necessarily want everybody to know what city we're from. So here, we're in Long Beach, right? So everybody who lives in Long Beach lives in LA County, the purple circle. And everybody who lives in LA County lives in SoCal. SoCal right here. You guys will see SoCal. Okay, so notice that there's people who live in LA County who do not live in Long Beach, right? And there's people who live in SoCal, like the people in San Diego, Riverside, Temecula, I don't know, all these other cities, they don't live in LA County, right? So these are all the people like a -1,000, -27. I'll get to that. Thank you for asking that question. Okay, the next one is rational numbers. And I like to say rational numbers are fractional numbers, right? So these are all the numbers that you can rewrite as a as a fraction. I know it does kind of. Okay, so here, this would kind of be, so if this is Long Beach and this is SoCal, LA County, this is SoCal, maybe yellow is California, right? And then green would be like the United States, and then orange is probably like North America. Notice there's people out here, right? Not these numbers, sorry, this is an example that I was using with another thing. So there's numbers out here, like there's people that live outside of North America, right? There's people that live inside North America, but not in the United States. You see how this all works. So this is what I'm using as an analogy. So rational numbers are all the numbers that can be written as a fraction. Irrational numbers are numbers that can't be written as a fraction. Like what, Miss Johnson? Like root 2. So irrational numbers are the numbers inside the green, but outside the yellow. Inside the green, inside real numbers, but outside yellow. Okay, so those are numbers like root 2, pi. You haven't met the number e yet, right? There's a number called e. You haven't met them yet. There's 5 root 3. There's 2 minus root 2. Any number that can't be written as a fraction. So most of these numbers are special numbers like pi and e, and then square root numbers. Okay. Today we're going to talk about the numbers that are outside the green circle that are also called complex numbers. So all of the numbers that are complex have to do with the I, and we're going to talk about him today. So let's get moving. Okay. So just remember that the irrational numbers are numbers that can't be written as a fraction, meaning irrational, like not rational. Rational, like a ratio, number like a ratio like 2 to 4, 3 to 7. Those are all numbers that can be rewritten as a fraction. And then we have the real set of numbers. So real numbers is every number that you know to date. Okay, we're now going to talk about these other numbers, which are called complex numbers. Okay, so in the previous lesson, to be determined, you found that the quadratic formula gives the solutions to the quadratic equation x squared plus 4x plus 5 as -2 plus square root of -1 and -2 minus square root of -1. Remember, that was really funny to us, like, ooh, that's weird. Because up to date, we had always said you can't take the square root of a negative number. Well, you can, right? I said yet. So now today, because the square root of a negative number has no defined value as either rational or irrational, this is a mathematician. His name is Euler. I want to call him Euler because that's what it feels like I should say. But other mathematicians who have pronounced his name call him Euler. So I'm going to go with Euler. Euler proposed that a new number I equals to the square root of -1 can be included in what became known as the complex number system. So the neat thing that Euler came up with was, hey, once I define I being the square root of -1, a bunch of cool things happen, right? A bunch of really cool things happen. Miss Johnson, cool things like what? Well, I'm going to show you, and then you'll understand why I think it's cool, okay? So based on Euler's definition of I, what would the value of I squared be? What would the value of I squared be? Okay, so I squared means I times I, right? I try to make my little I with a little tail on it so that you guys aren't confused that it's a 1. So just keep that in mind. Like, why does her I look so fancy? It actually doesn't look fancy. Why is my computer going so slow? That's another question. Come on, you can do this. Look at that. See, when you believe in your computer, it does. Just kidding. All right. So I times I. Well, what is I, guys? What's I? What is I? They told you up here. Yeah, no, read it. What is I equal to? Yeah, oops, I crossed it out instead of highlighting it. Sorry. I really want you to say it out loud. That's why I'm waiting for you. Yeah, it's the square root of -1. Very good. So, Ms. Johnson, you just want me to multiply the square root of -1 times the square root of -1? Yes. What is the square root of -1 times the square root of -1? Someone say it. Someone say it. I know you know it. No, what's this? Like, here, let me give you a hint. What's the square root of 2 times the square root of 2? Yeah, it's the square root of 4. And what's the square root of 4? 2. What do you notice happens? Square root of 2 times the square root of 2 is just 2, right? So therefore, what's the square root of -1 times the square root of -1? It's 1. It's -1, sorry. It's -1. Very good. It's just -1. Very good. Does that make sense? Kind of, Ms. Johnson. Okay, so if it doesn't make sense right now, just hold on to it. We're going to be using this over and over again. So it has to do with the square root of 2 times the square root of 2 is just 2, right? Or another way to think about it is it goes like this. Yeah, that's the weird part. I know you guys are saying, but Miss Johnson, if I multiply those two together, I would get that. Yes, but if you think about it like this, right? If you think about it this way, the square root of -1 squared, right? Those two cancel and see how you're left with -1. That's the way I want you to think about it. Not this way. Don't think, oh, multiply the -1 times the -1 and I get a +1. I totally understand why you said that. Very good. Very good. So yes, this is the one place that it's weird. The rest of the places are exactly what you expect. Yeah. Very good. Very good. You guys are asking really good questions. Okay. So write the introduction. Wait, with the introduction of the number I, the square root of any negative number can be represented. For example, the square root of -2, you can now rewrite as the square root of 2 times the square root of -1, which you all know. What's the square root of -1? Oh, that's that I thing. Yeah, so it's now I. Same thing goes here. The square root of -9, you're going to separate out the -1. What's the square root of 9, guys? And you're like, oh, that's 3. What's the square root of -1? Oh, that's I. So here, what they're saying is the way you think it should work, it kind of intuitively does work. Okay. So let's try this one. I'm going to do this one with you, and then I want you to try this one by yourself. So if I think about the definition of squared, it means times itself. So I'm going to square root 2. I'm going to multiply square root of 2i times the square root of 2i, right? And I'm going to multiply those together. Hold on a second. There it goes. So I'm closing out all the stuff on my app. So when I multiply these two together, I'm going to multiply the root 2 times root 2. What's root 2 times root 2? Good. It's root 4, which is equal to 2, correct? It's root 4, not 4. It's not equal to 4. It's root 4, which is equal to 2. So I'm going to write 2. And what's I times I? What's I times I? Well, that's I squared, Miss Johnson. Good. And over here, we defined I squared as who? What's I squared equal to? I need to write this big so that you guys all see it. What's I squared equal to? -1. So put this in like a little like bubble in your head. Every time you see I squared, it's -1, right? So this is just 2 times -1, which is just -2. Got it? Very good. Good job. I'm just collecting some participation points for you guys. Okay. All right. So can you all try this one? I'm going to have you pause the video and I want you to try this one. Okay. Simplify it till its very end. Okay. Try that one. Okay. So 3i times 3i. I'm just going to multiply 3 times 3, which is 9. You guys comfortable with 9? Good. And then I times I. What's I times I? Very good. I squared. But what's I squared? Very good. -1. So therefore the answer is -9. Very good. A couple of people checked that in already and knew that that was the right answer. Very good. Yes, it would be -9 because of that -1. Very good. So the cool thing that I like to tell people is if it works in number land, it'll work in whatever land. So right now my integrated 3 students are learning about polynomials. And the thing that I keep saying is because it works in number land, the way you divide, then that's how you divide in polynomials. It's not perfect, but it's how you would apply that same understanding. So this next idea says numbers like 3i and root 2i are called imaginary numbers, okay? Because they have I parts, right? They have I parts. Numbers like -2 minus I and -2 plus I that include a real term and an imaginary term are called complex numbers. So if you think about the idea of complex, something that's complex is like it's mixed with stuff, right? So I think about the complex things, they're mixed, and it's mixed with real and imaginary. So these numbers here, they only have I parts, 3i, root 2i. Therefore, they're called imaginary numbers. Here, because we have a real part, -2, and an imaginary part, -I, these are mixed, right? So we call these complex numbers, okay? Don't worry about the definition. Just get used to hearing this word complex and thinking, oh, that has I stuff in it. Does that make sense? So complex numbers are not real numbers. They do not lie on the real number line that includes all of the rational and irrational numbers. Also note that the real numbers are a subset of the complex numbers, since real number results when the imaginary part of a plus bi is 0, that is a plus 0i. So remember my big circle, right? If you look at my big gigantic orange circle, part of it is made up of that green circle, which is the real part. So complex numbers are made up of a real part and an imaginary part. The real part is the green circle, okay? So again, this is like a lot of definitions. Don't worry, I'm going to explain everything to you. You'll be fine. So operations, meaning adding, subtracting, multiplying, dividing, all those guys, with complex numbers follows the same properties as real numbers. This is how Ms. Johnson, they are saying this in a fancy way. Ready? I say, because it works in because it works in number land, right? It works in complex land. So how you think you should add them is how you would add them, is what I'm saying. How you think you should subtract them is how you subtract them. How you think you should multiply or divide them is how you would multiply or divide those numbers. Okay, there's just a little bit of a like pay attention to this one part to make sure that you're getting it right. So, but there are a few things to pay attention to, like when adding or subtracting two complex numbers, the real parts of the numbers are like terms, and the imaginary part numbers are like terms. So wait, you just want me to add these as if they're like terms? Exactly. So for example, 3 plus 4i plus 5 minus 2i is equal to 8 plus 2i. Wait, where'd they get the 8 from? Where'd they get the 8 from? So this is your observation skills. So as a mathematician, your job is to observe and say, wait, I wonder if that 8 came from blah, 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 blah. So where do you think this 8 came from? Exactly. It came from the real part. 8 is a real number. So it came from the real 3 and the real 5, making 8. Everybody okay with that? Wait, Ms. Johnson. So wait, can I ask you a question? Do you think I've taught you anything new so far? Wait, so you just want me to add 3 plus 5? Yes. Do you have, in reality, have I taught you anything new? The answer is no. Yeah, I haven't taught you anything new. Yes, I am making you apply something that you've known to something that is new, right? Does that make sense? So I'm making you, I don't know, maybe you're playing baseball, and instead of batting right, I tell you, okay, now turn around and bat left. So it's not new. It's just you're applying something that you already know to something different or new. Does that make sense? So I haven't taught you anything new. So, okay, 4i and plus -2i, is that how they got the 2i here? Is that how they got the 2i? And you're like, yes, Miss Johnson. Okay. So if you want to line them up vertically, like a polynomial, like up and down from each other, you can do that. When complex numbers are subtracted, it helps to change the sign. So Miss Johnson will always add the opposite. So I'll put a big O plus sign here. I won't do it here because I don't want to mess up our notes, but I'll put a big plus sign here. Hold on a second. I'll put a plus sign here and change everybody to their opposite. Does that make sense? So now it's -3 plus 5i. Does that make sense? So that's how they got this. And then again, that's what you know. So I want you to try these problems here. Pick A or B, pick C or D, and try each of these so that you can be reassured like, oh, I do know how to do this. And then you'll understand why students tend to like this section. Okay, so I told you to pick one and pick one. So your strategy for this is almost like ignoring the one that you're not paying attention to. So here, I'm just going to ignore the i's, and I'm going to go 13 plus -12. And then so I get 1. And I get 2 i's plus -5 i's is -3 i's. And I say it like that on purpose because I want you to remember that 2i just means 2 i's, like I plus I, right? So 2 i's, right? 2 i's minus 5 i's is -3 i's, right? Okay, so I actually will do all of them really quick just because I think it'll be fast. -7 plus 3 is -4. And 12 i's plus -6 i's, what did you guys get? What's 12 i's plus -6 i's? Yeah, 6 i's. What does that say, Miss Johnson? That's too messy. There you go. So I got -4 plus 6i. Same thing goes here, except for now, Miss Johnson, she forgets minuses all the time. So I'm going to come in and change these all to their opposites. So instead of this being a 7, now it's -7. Instead of this saying -3i, now it's +3i. So now I just add them like normal. So 8 minus 7, that's 1. -i plus 3i, that's plus 2 i's. Okay. Someone just said in the chat, a spider has 6 eyes. Does it really? I didn't know that. I know a fly has a bunch of eyes. Oh, okay, perfect. Yeah. Yeah, so if you make a mistake, that's not a big deal. The big deal is if you don't go back and figure out why you made that mistake, right? Okay, so again, I'm going to go through and change my minus to a plus, and I'm going to add all the opposites. So this has -9 plus -9, that's -18. And I got 4i plus 4i is 8i. Okay, so adding and subtracting isn't anything like, man, Miss Johnson, this is like, right? Nothing here is like, this is so difficult. My brain hurts, right? There's nothing here that's like, right? Not so. Okay, so multiplying complex numbers is the same as multiplying irrational numbers like x plus 5 and x minus 2. Do you remember how we used to do this? Well, we're still going to use that box, right? So with one step added, the only time I squared shows up, just remember that he's equal to -1 and then simplify as necessary. So for example, if we multiply 4 plus 2i, 4 plus 2i, and 3 minus 5i, it's just that open area model, right? The box. So we go 3 times 4 is 12. 3 times 2i feels weird, but it's exactly what you think it is, which is 6i. Same thing goes here. And then you get down to here, which is -10i squared. And you're like, Miss Johnson, I squared -1. Very good. So -10 times -1 is +10, which is what we get here. And then you simplify, right? So 12 plus 10 is 22, and then that's it. Okay. So what I want you to do right now is I want you to try using the area model for this one and see if you can get the answer that when you simplify. Now, when you simplify it, it should be in what we call complex standard form, which looks like this: a real number plus imaginary number. And you're like, Ms. Johnson, you just pointed at a minus sign and you said plus. So whenever I say plus, I always think of this as just being a negative 14i. So yeah, I do mean plus. Okay. So here, what I want you to do is try, I think I will have you try B, because there's a lot of negatives that you're going to have to keep track of. And you could try A on your own later on, but right now I want you to try B. So go ahead and try that. Okay. So when you're multiplying, you'll notice how similar it looks to the stuff that we've done in the past. So I just draw my box or my open area model, and then I get 10 minus 3i and 4 minus 6i. Right, 10 minus 3i. Okay. Then you just multiply. Multiplying is not a big deal. This is 40. This is negative 12 i's. This is negative 60 i's. And this is, okay, so I do this one thing at a time because my brain is like, right in the beginning. So negative times negative is positive. 6 times 3 is 18. And then I squared, right? But 18i squared is just equal to, anybody know? 18i squared, what is it equal to? Come on, y'all. What is 18i squared equal to? No, I squared. I'm focusing on the I squared part. What is I squared equal to? Yeah, it's -1. So what is 18i squared? No, not 9. Yes, -18. Very good. So if you didn't get this, if you didn't realize, okay, so let's say you got here and you just forgot that I squared was equal to -1, not a big deal. But if you were to try to write it in standard form, real number plus imaginary part, you would have realized, like, where does this I squared guy like fit? So 14 and this minus 18 is going to show up. 40, sorry, I said 14. 40 minus 18, I believe, is 22. So my answer is going to be 22. And then negative 6 i's minus 12 i's. Well, that's negative 72 i's. Okay. And so there's your answer. Real imaginary part. Real imaginary part. Any questions on this? Anything here that you're like, wait, I still don't get it? So again, I'll ask you again. Have you learned anything new? And you guys are like, yes, Ms. Johnson, I squared equals -1. Yes. So besides I squared equals -1, have you learned anything new? Yeah, no, right? Okay. Very good. So it says these two complex numbers are called conjugates. So I don't think I've talked about conjugates in this class, but I've talked about it, interestingly enough, in both my 12th grade class and my 11th grade class, for sure. So these are called conjugates, okay? So I want you to think about the word conjugates, and we actually pronounce it differently when we're talking about verbs in Spanish, right? When we conjugate a verb in Spanish, so I'm going to write them all here. We go comer. Sorry, that's my favorite verb. Just kidding. So it's como, comes, come, comemos, and comen. Okay, so here's all my verbs, right? When you conjugate a verb, there's parts of it that stay the same, C-O-M, and parts that change. ER changes to O, ES, E, MOS, and N, right? So this depends on who is doing the eating, right? Because that's what comer means, right? So same thing with conjugates. Conjugates, some parts stay the same and some parts change. What are the parts that, I know, right? What are the parts that stay the same here? What are the parts that stay the same? Yeah, you can name them. What parts stay the same here? Yeah, the 4 stays the same, Miss Johnson. Good. And the 2i stays the same, Miss Johnson. Good. What part changed? What part changed? What's the only thing that changed from here to here? Yeah, the operation in the middle changed. So when you conjugate a verb in Spanish, the ending changes, but sometimes the middle changes depending on if it's an irregular verb, right? But here, our operation changes. So do you see how these two are also called conjugates? And technically, these are called complex conjugates. And you can all know why it's called complex. So what I want you to do is I want you to multiply both of these, and I want to see if you can recognize what is happening. So go ahead and multiply both of these. Don't forget about your I squared term and tell me what your final answer is. So go ahead and practice this. Again, this is one of those things that looks really complicated, but when you actually do it, it'll make sense. So don't neglect your practice time here. Okay, so I don't have time to do both of them, so I'm only going to do one of them, and I'll do this one down here. So I'm going to multiply this as if I don't recognize anything. I'm going to pretend that I don't see that they're complex conjugates. Okay, so I'm going to multiply 3 times 3, that's 9. 3 times 5i is 15i. Negative 15i. Does anybody see what happens? Negative 5i times 5i is negative. 5 times 5 is 25. And then I squared, yes? Does anybody see anything that's going to happen? What do you see that's going to happen? What do you see? Take your young observation eyes, like observable, very young, very good at observing. What do you see that's gonna happen? Yeah. First of all, your 15i and your minus 15i, they cancel. Very good. Huh. I wonder if that'll happen with all conjugates. And you're like, yeah, that would happen with all conjugates. Yes, that is true. It'll happen with all conjugates. Now, what about this minus 25 I squared business? What does that simplify to? All right, guys, come on. Remember, this is the one thing that's different that you learned. What is I squared? Very good. So what's negative 25 I squared? Yeah, it's positive 25. Wait, Ms. Johnson, why is it positive 25? Because negative 25 times negative 1 makes a positive 25. Very good. So when I simplify this all out, what numbers should I put here? What number goes right here? What's the answer? What does this all simplify to? Come on, guys. What does this simplify to? What is left? Yes, I can tell you the answer, but I want you to tell me. What's the answer? What's left? No. Remember, how did we get 22 minus 72? What did we do at the end? We added, correct? So what do we have left to do? What's left? You tell me, which one should we do? Should we add or should we subtract? Good. What's our answer? No, our answer is just 34. You guys, I don't know what happened, but you all told me different answers. Okay. So at the very end, so remember when we multiplied like x plus 2 times x minus 7, all you would do is just add all the terms together. So that's all we're doing. So 59 minus 59, that cancels. This guy simplifies to 25. 9 plus 25, it's 34. Everybody okay with 34? Does everybody see why it's 34? Okay, good. Then the next part is, okay, Ms. Johnson, but you said we had to have a real and an imaginary part. I do have an imaginary part. It's 0. I know you sometimes when you guys overthink things, you take something very simple and you're complicating it. Remember, my goal for today is to keep making you say, so really this is just like blah, blah, blah. Yes, this is just like blah, 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 right? Okay, so this is exactly like just multiplying a binomial times a binomial, like x plus 2 times x minus 7. Okay. So you should notice that both of these, when you do both of them, your these two will cancel out, right? And that's the reason why conjugates are kind of neat. We will use this idea a lot. Okay, we will use this idea a lot when it comes to, you know, this one section later on. And for you guys, it's later on. Okay, so just keep this in mind. I'm going to use this in the future. Okay, so so it says, I just want to go through all of this. Okay, last thing. So the fundamental theorem of algebra revisited. We talked about whenever we are looking at a polynomial of whatever 10th degree, that means it's going to have 10 roots. Now here, notice it doesn't say what kind of roots those are. And now you know that some of those roots could in fact be complex or imaginary. Okay, and so so it says, based on your work in this task, I'm finishing up right now, do you believe that this theorem holds true for quadratic functions? That is, do all functions of the form ax squared plus bx plus c always have 2 roots? And the answer here is yes, right? And sometimes those roots are real, and sometimes those roots are imaginary or complex. Okay, hope that makes sense. Thank you for listening.